Good afternoon, everyone. Welcome to our third technical talk by the Institution of Structural Engineers, Southern Region. We've got with us Professor Richard Walls. He's an expert in structural fire engineering, and he'll be presenting this talk today. It's a very interesting topic. I've been involved with it myself before I ran away from it. But then, yeah, so we're fortunate enough to have Professor Richard Walls here. I'll allow him to introduce himself and then he can proceed with the presentation.
Okay, good afternoon, ladies and gents. Welcome all. Hope everyone is doing well where you guys are. So I'm going to be presenting on the fundamentals of structural fire engineering today. It's good just scanning through the list of attendees. Greetings, I know a number of you in the room, so I hope everyone is doing well, especially those of you who I know. You're welcome to type questions as we go. Please feel free to put some questions at the side in the chat bar. I will see whether if as we're going, I can answer them. I will do that, otherwise wait to the end. We'll see how sort of the questions come around. Hopefully everyone can hear me. I see a comment about I cannot get sound, but the administrators in Jabula, etc., if there's any technical queries and I'm messing anything up, let me know. But hopefully we are all well. So when it comes to structural fire design, I find this quite great. A genius is someone who takes a complex thing and makes it look simple. An academic does the opposite. We academics normally take something and just make it vastly more complicated than it should be. Now, structural fire design is fairly complex, to be perfectly honest. However, I'm going to try at least keep it reasonably simple in terms of general approaches, because it can get quite hairy as you get into sort of stresses and strains, etc., down at fundamental level. So firstly, just going to introduce fire safety at Stellenbosch University. So we've got the first fire engineering research group at postgrad level in Africa. So we're focusing on a variety of topics: building response, fire modeling, full-scale steelwork testing, building code, informal settlements, investigations, design of industrial facilities, cross-laminated timber, fire modeling. We've recently also got into 3D printing, 3D printed concrete in fire, materials behavior, all sorts of stuff. So if you need fire engineering or structural fire design staff, let us know. We have a team of 8 PhDs and 8 master students, so a fairly big group. Some others, almost 20 researchers working on different topics when you've got postdocs, etc. involved. So if you need some staff, get in touch with me. We've got some good people who will be graduating this year. We have an MEng program in structural fire engineering, or just a more traditional fire safety engineering. 2 years full-time. It's a full research thesis. And then we've got fire safety engineering, structural fire design, and fire behavior. So those are full postgraduate modules, 15 credit modules. They are being done as postgrad modules as well. And just as a note, the structural fire design, the course that we are doing at the moment, like that I'm presenting here, we actually are running as a CPD event online with pre-recorded lectures. So if you want, we actually, with COVID, we extended the closing date that. So if you want to do a 2-day CPD version of the talk I'm giving with far more information I'm giving now, you can get in touch if you go on our website, or the search civil engineering short courses, structural fire design should be come up. Otherwise, just email me and I'll send you the details, rwalls@sun. We'll get there later, rwalls@sun.ac.za. As we've got PhD, we've got 8 PhD students. We have YouTube videos on structural fire design. So this is on our FireSUN. So actually I haven't got listed, Fire, then S, Stellenbosch University, the Fire Engineering Research Unit. We've got a whole variety of teaching materials. So you are welcome to go have a look at those if you are interested in finding out more. So when it comes to structural design, one of the key principles is passive protection. How do we specify passive protection? And it's quite an easy way to determine who specifies it on a project. Basically, the architect and the structural engineer stare at each other, and the first person who blinks gets the job. Now, the fire engineer already said it's not part of his or her scope, or hasn't even been appointed yet. So it's a major problem. And there's a lot of money you will see going into fire protection, but it's often the sort of gray area where is it the architect, the fire engineer, the structural engineer specifying it? But you'll see it's actually fundamental to structural design that should fall within our scope. We as structural engineers should be taking that and also getting paid for it because it's part of our scope and it's about load bearing. So we don't want someone who's not dealing with the load bearing system to start specifying it. So as an interesting question to ask, this is a picture of Cape Town International Airport. Imagine a fire in this building. Imagine what temperature would the steel in this building get to? What could affect this steel? What if we're going to use prescriptive, deemed to satisfy rules, but let's say now we were going to generate a real fire, a real event that could happen in this building. What would be a real event that we might need to design for? And so now, yes, you may have terrorist attacks. So those are always very difficult to design for. Those are more blast loads, but I'm talking fire loads, high temperatures. So yep, maybe you have a whole bunch of baggage that catches fire. So maybe you can have localized fires around the columns. On the roof level, imagine even a big fire now here at the bottom and the hot air rising up. By the time it reaches the roof, it's actually fairly cool. And you'll see earlier how it's very cool. The roof, when would the roof up here get hot? When would it get to the temperature at which steel starts losing strength? 400, 500, 600, 800 degrees Celsius. Not often. You'd need one hang of a fire in here, or you'd need the cladding on the roof to catch fire. You'd actually need the system, the cladding system up there to burn. Then maybe you'd start getting to the stage of being able to burn it. So, to affect the structural system. So let's start having a look at the overview. First, we're going to have a look at the role of fire engineers, structural design, structural fire engineers, and structural fire design, building requirements, design fires and building loading, and then structural response and the effect of fires on building steel, concrete, composite, timber, etc. So we're going to go through the main structural systems and look at how to design them. And then also saving money on passive fire protection, because a lot of this comes down to money. You can very easily engineer a safe system by just slapping protection on anything, but it's going to cost time and money to get that done. So a major question to ask with structural fire design is, what is failure? Now imagine that your building which you've designed burns down and you arrive on site and it looks like that. It's still standing. Everyone got out alive. You need to demolish it now. It had a very severe fire. There was large amounts of fuel load in the room. Is this success or is this failure? And that's one of the challenges, is this is a very different limit state to what we're used to doing. We're used to, all right, reusing it immediately afterwards. A successful design may be something that is potentially condemned if it's the fires in way in excess of the design that, well, what it should have experienced. So to what extent do we allow damage? And that is a bit difficult to define. And you'll also see why, because our fire scenarios and the loads we design for are just so arbitrary that it becomes a problem. So now this structure here from structural resistance may actually be considered a success. Yay, my building's still standing, no one's dead. We'd either have to repair or replace the structure, but everyone got out. Compartmentation, well, that depends now. As my structure deflects, perhaps I had a wall here that was preventing fire spread from one zone to another. But as I got large deflections, suddenly gaps opened up, especially if it was on the floor above, and then my compartmentation failed. So then there was fire spread throughout the building. Perhaps then I have a failure. So we've also got to look at, what do you mean by pass? What do you mean by failure? What is success? So let's have a look at the role of the structural fire engineer. What are you saying that when you sign those forms saying, yep, this is suitable for requirements? This is the European guidelines, but the South African ones are fairly similar. The Commission of the European Communities outlines the general requirements of construction work subjected to fire conditions as the load bearing capacity of the construction can be assumed for a specific period of time. Mr. Mrs. Structural Engineer, you can tell me this has a 60-minute fire resistance. Okay, great. The generation of and spread of fire and smoke within the works are limited. The spread of fire to neighboring construction works is limited. We have some amount of influence on this, but this also falls a lot within the fire engineer's role. the sort of the fire consultant's role. He or she would often be generating that. And then occupants can leave the works or be rescued by other means. And then the last, well, especially these last two, sorry, this would often be then in your layouts dealt with between the mechanical engineers or the fire engineers and then the architects in terms of egress, evacuation, access, etc. So what is failure coming back? Now, SANS 10400 Part T, which then refers to our testing standard, SANS 10177, especially Part 2, these are the requirements that a system has to obtain. So let's say you build a wall and you say this has a 1 hour fire rating. What does it mean? So for instance, if you had a wall or floor, firstly, it has stability, strength, and structural resistance. After a given fire scenario, it can still carry the load. Then integrity, the passage of smoke and flame through the slab must be prevented. So your slab may be strong enough, but let's say it cracks. Where it cracks, smoke and flame can pass through, therefore it's failed. It has failed an integrity failure. Then insulation, this limits the amount of heat that is allowed to pass through the slab. The aim is to prevent spontaneous combustion on the unexposed face. So if you've got a wall and you've got wallpaper on the far side, the wallpaper doesn't spontaneously ignite. The average temperature rise on the upper surface or the unexposed surface may not exceed 140 degrees, and the peak temperature may not exceed 180 degrees Celsius. These are actually quite conservative. Most materials don't spontaneously ignite until much higher temperatures, but you would check against this. I like the REI from the Eurocode. This is not in SANS, but it's useful just lettering to see there are 3 distinct criteria. A column would only have structural resistance R. But for instance, a non-load bearing compartment will be EI. It needs to have 60 minutes integrity and insulation resistance, but even though it's not carrying load on it. So when we are trying to now provide those resistances, there are various ways. Prescriptive, performance-based design or rational design. And rational design is a terrible word in South Africa. Rational design in fire engineering terms in South Africa means I want to break the code and get a cheaper solution, and I'm going to cherry pick from another code to get there. There are some good rational designers in this country, but a lot of the time rational design simply means I want to break the rules and I'm looking for, you know, some excuse from a clause from a different code. But so you've got prescriptive design, rational design, and everything in between. So this is in the European code, the different guidelines for the range of solutions. And you can see you can have 10 different solutions to one problem. On the one hand, you've got tabulated data. You phone up the instrumescent person, takes 5 minutes, or you look it up a code. It's normally a bit conservative. You slap on some board, paint, etc., job done. The other side is the really, really detailed performance-based design. You phone the university, takes 5 months. You may save a lot of money on the construction costs, but you're probably going to spend a lot more on the consulting costs. This is really only your high-rise buildings in inner city London, fancy office blocks, etc., where there's a lot of money and you really want to push the bounds on structural design and to get to innovative architectural systems, etc. And then you've got everything in between, because on the one hand, you've got prescriptive, on the other side, you've got rational, and a lot of it is linked to the fire scenario. And we're going to have a look at what that means soon, because performance-based or rational structural design is a little bit different to what you would be used to so far. Because first what you do is you develop a fire scenario. So what is my time temperature curve? How hot is the fire and for what period of time? Then once I've got a fire, I work out how hot is my system. For instance, this is just a drywall system. I've got 2 boards and a wall stud. How hot is my system? Then once I know how hot my system is, I design the system, calculating structural loads, calculating induced forces, and designing the member at elevated temperatures, and we run through it. So most of this is done on the standard fire. So whenever you hear 30 minutes, it's 30 minutes of the standard fire. And this code was developed more than 100 years ago, almost 120 years ago. And cynically, it's the rate that 3 guys could shovel coal into a furnace. It was an arbitrary benchmark. Our entire structural engineering community is based upon it. but it is semi-arbitrary. It is not necessarily the worst, the best, anything else. It's very useful. It's a useful benchmark, but just be careful of it not that precise a measure of fire exposure. So now that's our standard fire, and everything is related to that. And can it survive 60 minutes or 120 minutes of this time temperature curve? And you do also get external curves, hydrocarbon curves. So the standard fire, after 5 minutes, it's almost 600 degrees. After 30 minutes, 840. After 120 minutes, it's 1049. So it's a fairly intense fire curve. You've got to stay at those temperatures for this period of time. So it's a raging inferno. So now, when I showed you the Cape Town International, the airport, to get to those temperatures at roof level, you would literally have to park tankers inside there and continuously release fuel into that hangar to get it to that temperature. So it's such a big open space and the heat would dissipate so fast. So that's where we start looking at different fire scenarios. But before we get there, let's have a look at a video of how do you actually test? What does it look like? So this is just a door test. It's speeded up. So this is a furnace. Now, inside the furnace, it is following the time temperature curve, standard fire curve. It's got burners and a control system managing it. This door only lasts about 10 minutes or 15 minutes. So it progressively bowed away and failed, and then it had flame through. So what else does failure look like? So let's have a couple of looks. This is a timber system. And after about 60 minutes, it eventually burned through. So this actually had a 60-minute. This is now an integrity or insulation failure. Large quantities of noxious fumes being emitted from a system with a combustible internal layer. There's flame through around the side. There's flame through at the bottom, door on the inside. And then this is the door I showed you earlier. It turned into a banana. There's a door, it failed at the top, burned through. So we did this work with Ignis testing. They're down here in Cape Town. So that is what furnace testing looks like. You put a door wall system in a furnace, and then you run the time temperature curve, and then you measure what happens to it. Can it then carry the load, etc. But one thing is that in real life, fires are different. You have ignition, it heats up, then it sort of gets warmer and warmer, and then you get to a transition where you have flashover, where it suddenly heats up, it gets to maximum temperature. It's normally at this stage limited by how much oxygen can get into the room, and then it decays. So often you have actually a flat period in the middle. But you have peak temperature around 1,000 degrees, decay phase, and this is different depending on your geometry, your fuel load, your boundary conditions, etc. But also one thing, sometimes buildings collapse during the cooling phase. The standard fire I showed you earlier was permanently heating up. It never cooled down. Well, then you get a 60-minute rating, great, and you turn off the furnace and you walk away. You should actually check how does it cool down, because sometimes what happens, something heats up, expands, sags, and then when it cools down, it contracts, induces tensile forces and snaps connections during the cooling phase. So there are curves that have been developed to try capture that. For instance, you've got your Eurocode parametric curves, where you have a heating phase and then a cooling phase based on the geometry, based on the ventilation, based on the fuel load. This is a very different approach. This looks at a burnout fire. So if all the fuel in my office, shopping center, library were consumed, how hot would it get and how long would it last? And you design for that. You're not designing for 30 or 60 minutes of a fire based on code. You're actually designing for my occupancy and my room. Would I survive this fire? So you can get fairly different answers depending on your approach. And often this is done simply because there can be such large savings in cost while not compromising on safety, because you know that the worst fire that could occur, you've still designed for. But you can also get other fires. Now, in the Cape Town International, the airport, you would have a localized fire. You wouldn't get to flashover. You wouldn't get to full room involvement. So you'd rather have a distinct fuel package burning near a column or a beam or something. And so you can design for that. And so then you can actually generate a fire and then work out how much energy is going into your column and then calculate the temperature of the column. You may also have traveling fires. in big open spaces, you get traveling fires where the fire just progressively moves through the building. And once again, the temperatures are much lower because the heat keeps escaping, so you don't have necessarily the same buildup. So designing for the fire in your large open plan office, you may get to a sort of a more cost-effective solution. So standard fires are quick and easy to generate. The fire department understands them. Everyone can talk the same language. Localized fires is when you can't have flashover, you can't have full room involvement. And then parametric fires try capture real fires. You can also have computational fluid dynamics and various other types of fires you can generate. So let's have a look at that. What is a fire? Now, this was some research we'd done previously. This is an informal settlement dwelling. And this is what happens when you get to flashover. There's suddenly full room involvement. Flames come looking for air. The entire room, every combustible surface is burning. You have 800, 900, 1000, 1200 degrees Celsius in that room. And the length of time it'll last is dependent upon how much fuel and how much ventilation you have. And so these graphs are actually the temperature. And then we simulated that with software, but within about 60 seconds, you got to flashover. Within 60 seconds, the entire room was on fire. And temperatures over 1000 degrees Celsius, there was a software prediction model. The standard fire is different. The standard fire heats up slower, depending on your geometry, but then will continue on. This was a very, very small dwelling. But this shows the difference between a burnout fire, fuel load, ventilation, etc., and a standard fire, which is a time temperature curve. Remember, standard fire as a benchmark, burnout fire is actually considering of your actual structure. But now, also, why would we start considering these different fire scenarios? A higher standard fire rating generally gives a better fire resistance. However, there are shortcomings to the method. A report investigated the detail regarding 22 fire-induced collapses in multi-story buildings that occurred over that period in steel, concrete, and masonry buildings. It noted of all the failure mechanisms in real buildings, the majority of them could not have been predicted by standard fire tests. When most buildings fall down in a fire, it's because of a failure mechanism that is not identified by standard fire tests. Normally your connections, thermal expansion, where things heat up, enlarge, and then knock columns over, snap connections, etc. World Trade Center 7 was a snapping of a connection causing pancaking. Structural interactions and connections play pivotal roles in the modes of failure. In fact, the authors note that connections are generally recognized as the critical link in the collapse vulnerability of all structural framing systems, whether or not fire is involved. If a fire breaks out in your building, the building comes down, chances are it's your connections that fail, yet we put 90% of our effort into putting paint on beams. So what is failure once again? That's the challenge in terms of defining failure, because it is so difficult. That's why we have simplified rules, because predicting the sort of behavior, complex beam column behavior, connections that were pinned, which become towards fixed, etc., becomes an interesting scenario and something to deal with. So let's start looking though at how would we go about doing this? How would we actually start getting to a solution? One of the things is that our loading is very different at the fire limit state. So normally ultimate limit state, 1.6 live or imposed load, 1.2 permanent or dead load. So we've got a ultimate limit state. During a fire, chances are the worst imposed load in a 50-year period will not be there. And it will also get burnt up during the fire. So instead of 1.6 imposed load, we're down to 0.5. It does range between 0.3 and 0.8, depending on which code and occupancy here, but it's normally around 0.5. So we're at about a third of the imposed load we're using, and then just a little bit less on the permanent load or the dead load. So that means we've got quite a lot of residual capacity. This means that during a fire, we can consider significantly lower loads in our building, especially for steel buildings. Hence, even though structural systems become weaker, they have to carry less load, so maybe okay. So let's start having a look at these systems. Let's look at steel, concrete, timber, composite, etc. So steelwork is where the big money is. And one of the reasons we often don't see high-rise steel in this country is because of the cost of passive protection, amongst other things. It is possible to have unprotected steelwork in a fire. If it fails and it doesn't influence anything, well, so what? Critical members need to be protected in certain types of structures. Only critical members in certain types of structures is composite floors. I'll get there later. Protection of steelwork is done using boards, intumescent paint, spray-on products, concrete encasements, etc. Connections can be very important. Passive protection is expensive, so careful design can significantly reduce the cost of passive protection. The next slide is where you can make your client like you. So this is some rough costing per meter on 3 different column sizes. Now have a look at the cost of an intumescent paint. And this is 2015 pricing, so it's gone up since then. So for our rating, the paint costs more than the column. If we now, for instance, a UC 203, 203, 46, that's the rough cost per meter of the column. We go to a 2-hour fire rating, it's 50% more than 50% more just for the paint. The paint is costing 1.5 times the steel. And then depending on the size, you can see now the cost varies. And this is linked to how fast does it heat up. And sometimes you will have a cheaper solution with heavier steel and lighter paint. The paint may be a bigger concern in terms of optimization than the paint itself. Yeah, so optimize the paint usage by changing your steel geometry. You may have a better solution. Thin steel sections heat up fast. So let's have a look at how these systems work. So this is a piece of equipment at Stellenbosch. So this is used to simulate fire exposure. Those radiant panels can get above 900 degrees Celsius. And then we subject, this would be a typical boarding type system. So it's just a passive layer, nothing happens. It just stays there and gets hotter and hotter. This is a different boarding system. Maybe releases a little bit of moisture, but in general, you see virtually no change. This is an ablative coating on a on cabling to prevent the cabling from burning. So you have to protect your cabling if it's critical. This is a paint on a timber. So you do get paints to protect timber. This paint was under R&D phases, actually failed. So initially you'll see it charring and expanding, but then it didn't char enough to prevent ignition. This is intumescent paint. So you can see as it heats up, it actually expands. There's a chemical reaction causing it to grow, and it forms a char layer at a couple of 100 degrees Celsius, so before and after pictures. This is a pipe collar, so if you've got a penetration through a wall, this will then close up that opening to prevent fire spread. You'll see we didn't run the experiment for long enough to close it up. This is then for closing your sort of penetrations, your bigger penetrations. You've got a non-combustible substrate and an intumescent on top. And then you can just see how it grows as it's heated up. And this is, if you've got a penetration, it's like a putty. So there's a plastic box and you put a putty on the inside, and then it protects the putty from, protects the plastic box from melting. So this is quite a cool way of protecting your penetrations, because as soon as you've got a penetration, you've got a weakening that the fire can pass through. But this side, you'll see that the fire can go around it, so it just melts the plastic. So had the plastic been unexposed, it probably would have been fine, but the plastic was exposed here, so it got melted. So why do we put products on steel? It is to prevent the steel getting too weak. So for instance, up to about 400 degrees Celsius, we've got almost all the steel strength. And then the temperature drops quickly after that. So what we do is we try to have a temperature we limit the steel to. And you will sometimes hear a critical temperature of 500 or 450 or 600 being listed. Those are approximate based on certain assumptions, but ultimately we're trying to keep the strength to a certain level to carry that fire limit stake load I showed you earlier. And as you move from 500 to 600 to 700, the temperature drop is fast. So that's why 50 or 100 degrees Celsius can be a very much more expensive passive protection system. So what you want to do is have your column heat up, your beam heat up as slow as possible. So you want a small perimeter and a thick steel. So a section with fire from all around will heat up much faster than a a beam or column with a slab on top and box exposure. The box reduces the perimeter. So you can have less passive protection with lower perimeter. So you want to keep short, stocky sections, which normally goes against what we want to do because we want a high IX and a high IY to prevent buckling. But that's unfortunately the nature of it. But what we're trying to do then, for instance, if you've got unprotected steel in a parametric fire, it would be there. Now we add on some protection and we drop it from, let's say, 830 to 550, and we find, all right, at 550, it is sufficient. So that will then, that's why we add passive protection, to drop that temperature during a fire so that our capacity is sufficient. And it depends on where our column is, how much load resistance it may be. For a normal column, at 500 degrees Celsius, it might be still strong enough, maybe 550, maybe 600. But for instance, you've got a facade column, which is just over-designed. It's there for architectural purposes and it's carrying very little load. You may find at 800 degrees Celsius, it's actually okay. And this is where rational design comes in, where you actually check what's the load, what's the temperature it can get to, and then you keep to that temperature. Where prescriptive design would be assume all columns are at X, 500, 550 degrees Celsius, and you specify for independent of the load levels. Concrete generally performs well. For concrete structures, the most important thing to ensure that there's sufficient cover to rebar. Concrete structures generally behave well in fire, although care must be taken with details and connections. This is from a fire damaged structure. It had to be demolished. You'll actually see the column is buckling. There's been extensive spalling and rebar being affected, but it stayed standing. None of the sort of connections, because it's monolithic, failed. But you can see the rebar heavily exposed, cracking along all the lines of the rebar, columns buckling. So this was a very severe fire, burned for extensive period of time, and structure had to be demolished. Where most structures you can put back into operation after damage. So concrete does lose fire up to about 400 degrees Celsius. It has its strength, and then the strength drops quickly. But it's a bulky section. So normally what happens is we lose material on the outside, but we just design our concrete as if it's a smaller section. So we just design it as a smaller section, and with heated rebar. So we work out the temperature. My rebar is now 500, and we design it. Where in sagging, chances are most of my rebar here is actually quite cool, and I have a reduced cross section, and I design it. So you can actually do a rational design on concrete as well for fire conditions, where normally you don't need to. Normally you just specify concrete. But is concrete always safe? Now here is some work done at University of Notre Dame, USA. This is a high concrete that is burnt, and bang. Concrete has moisture in it. High strength concretes can trap the moisture in. So you create steam, but the steam can't go anywhere until the pressure builds up and basically it explodes. So there are times where you do have to be a little bit cautious in terms of it. High strength concretes are susceptible to explosive spalling. And then also you have conditions where some materials do degrade. For instance, your post-tensioning, pre-stressing steels, your high tensile steels can permanently lose strength, so they can be a problem, so you have to look at them. And there's other areas where you may have to look at. I'm just trying to give you a sort of a very brief overview of structural fire design at this stage. Now, timber structures. Timber, as soon as you say timber and fire, everyone has a bit of a heart attack, because timber we see as firewood that you can bry on, not a structural material into most structural designers when it comes to fire safety. But timber structures with heavy members can survive severe fires. We actually had a furnace test which needed to last for an hour, and we needed dependable resistance. We actually put timber beams into the furnace rather than steelwork, because we at least knew what the capacity was, and if anything went wrong, it was okay. Whereas the steelwork was a bigger challenge to make sure it worked in case of a problem. So outer charred layers protect the inner layers of the structure. Timber fire design is done assuming that a certain amount of material is lost during the fire. So same thing as the concrete structure is that you've got a fire and the fire is exposed all around. and you progressively burn away the material. It progressively chars all this material. And depending on your species of wood, you lose about somewhere between 0.5 and 1. One's quite high, but somewhere between 0.5 and 1 millimeter of timber per minute. So after 60 minutes, let's say it's a low charring at about 0.5 mil, you'll lose 30 mils on the one side, 30 mils on the other side. So I will now have 30 mils less material, plus we have a layer of material that is decreased in strength. So we normally ignore it, and that's somewhere around 7 mils, give or take. So as long as our preliminary section had more than that area, we can design a residual cross-section to carry the load. So as long as this residual cross-section is bigger at the fire limit state, remember with a third or around a third of the imposed load, then you may be able to carry the load. So that is the basis for the design. Biggest challenge with this is now the timber is contributing to the fire load. So you used to, for instance, let's have a 60-minute fire rating, but now you have timber, your skeleton contributes to the fuel load. So maybe now is 60 minutes enough? So you may need to increase the fire resistance that's required, or what's often specified is some of the codes, you limit the area of exposed timber, so you limit the area of contributing fuel to the fire load. So there are ways and means of dealing with it, but timber is a growing material. We actually have a PhD finishing up his thesis on the design of timber connections and furnace testing, etc. So timber connections also become critical, because now you've got steel work and bolts, etc., that can be heated up. So he's doing some nice work there. Composite design. Composite is another area where you can save a lot of money. And the BRE Cardington full-scale test, amongst many others, showed that composite slabs behave very well in fire, even when steelwork is not protected. In this compartment, there was no passive protection on that steelwork. Temperatures got above 1,000 degrees Celsius, but nothing collapsed. So normally we say collapses 450, or 500, 600 degrees Celsius, a critical temperature. This got to 1,000 and it was still fine. Well, the gas temperature, the steel temperature, I can't remember off the top of my head. But the steel work got very hot, deflected, sagged, but the whole thing holds together and you get what's called catenary action. You have rebar in that slab that is protected, and it allows you just to hang your slab off the structure around it. So your loads pushing down are carried by a hanging catenary of resistance, provided you can guarantee the capacity of your primary beams. Then who cares if this beam fails? Well, it's just part of catenary. Yes, you're going to have to do quite significant repair after real fire, but the probability of such a severe fire is actually very low, especially in a sprinklered building. Now, here would be, for instance, a building you're designing. And so what you would do, this is a multi-bay structure, you would protect your primary beams. You would design as if the whole slab in the middle has failed, and you would not protect all those beams. They would be unprotected. You do not put a stitch of passive protection. You let them fail. You design it using a crack pattern. So traditional failure patterns, plastic analysis with catenary action involved, and you design it and you save 50% on your passive protection cost, relying on your perimeter beams and relying on your columns. Your columns are key. Your columns go, you're in big trouble. Columns, connections, etc. But your intermediate beams you're allowed to fail. So it would look like this. So you protect your primary beams, you protect your columns, you ignore your secondary beams. And depending on your geometry, you may have a 50% savings on your beams. So that can be a lot of money when I showed you based on those passive protection costings earlier. It's something to think about when you've got a multi-story composite structure. It's how to make them more cost effective and to provide a good solution. So we've been discussing rational design throughout. And as I said, there are various approaches. Most of them are based upon a column in a furnace. So what would normally happen is A real structure would perform as shown here. You'd have a fire in a distinct area. It would heat up the slab, beams, columns, there'd be deflections, etc. There'd be induced forces. As things expand, they induce very high forces, and it's normally those induced forces which cause failure. So as this slab pushes out, it causes major bending on a column, causes the connection or the column to fail. Whereas in standard fire testing, what we do is we assume that it's a simply supported column with a fire from all sides. So it's a very different scenario. So prescriptive design, it's a simply supported beam, simply supported column, no boundary conditions, no induced forces, time. On the other hand, then you get rational design, as I've shown here, with depending on what level you go to, you actually look at the structural interactions, the beams, the columns, the forces induced, etc., which requires progressively more time as you consider more and more of the structure. But it's those forces, those induced thermal forces, which govern failure. And you may, for instance, then as a structural fire designer, need to go back and identify key elements. So for instance, this is a floor plan, and this is from the UK. So everyone needed a 90-minute fire rating. Great. Now it's code compliant. But if you run through the design, you may find, for instance, there are critical members. For instance, if these beams expand, they're going to put a lot of lateral loads on that blue beam. So it needs a little bit more capacity. It's a critical member, high lateral loads on minor axis. So we increase its resistance. We give it a little bit more capacity. Same thing, this beam expanding may push on that one, and these ones that say are critical. So we may find that strengthening key elements increases the or reduces the chance of failure. Same thing, going and have a careful look at your columns and your beam column connections, and putting connections that can accommodate heavy movement all makes a major difference to this sort of testing. So just in summary, to be perfectly honest, most structural engineers in South Africa currently have very little knowledge about fire design. I come out consulting background and know that as a design consultant, most of the time you just leave it for the fire guy and they sort things out, and it's not your problem. And so that's one of the areas where we have a significant mismatch in our system. It's part of our package. Keeping the structure up is part of our design. This is an extra limit state. The thing is, it requires quite a bit of knowledge, or quite a bit of analysis to get there. So get specialist assistance on critical structures, especially when using steelwork. Steelwork can be safely used in fire if one knows how to, because you can start saying, do I need to protect everything? What is critical? Where do I focus my time and effort? And are there members that I can allow to fail and reduce the cost? Then our new South African Design Steel Code, SANS 1160 Part 1, which will be released soon. I'm leaving it as is, but I still don't know what the definition of soon is, because it's been in process for a fair while. So maybe someone else on this call knows more, but it's been soon for a fair while. But alternatively, we could actually just use from the Canadian code. They have a fire design annex. The updated 10162 is from Canada. And so we can adopt it straight away, and it's exactly consistent with our modern code. So we do have a fire design annex from them. So we don't have a structural fire loading code. However, our codes are sufficiently consistent that we could use the European codes or the American code. So one thing with the codes, the Europeans write great technical codes by academics, so they're so difficult to understand. The Americans normally have far simpler approaches, far easier to use for design consultants, but also have less bells and whistles. So it depends on kind of what you need. Okay, structural engineering with good fire knowledge are needed to produce economical structures, but the client needs to realize as a skill the consultants must be paid for. If you're going to be consulting and doing calcs and taking liability, there needs to be consulting fees allocated to, and I think that's probably one of the biggest barriers to promoting and moving forward, is that there needs to be an approach in terms of payment and addressing these sorts of issues. So yeah, so coming back, does this steelwork need fire protection? The question I threw out to you earlier, and this is just before I wrap up. Well, it depends on what we mean by fire protection, what fire scenario and protection. So yes, a post flashover fire will not occur in this group. It's too big. The hot gases will rise to the roof and just spread along. You will never have a stage where everything here is burning unless you crash like I don't know, 10 tanker trucks in here, you light them all at once and you keep feeding them, then maybe you'll get to a 2-hour fire or 1-hour fire or something. But most of the time you'll have localized fires. You may have cladding catching fire, you may have terrorist attacks, you may have all sorts of things. But at the same time, if I was the consultant on this, I'd go belts and braces. You know, this is a national key point with a lot of unknown scenarios. So this is also in these main load-bearing elements, not the time to go light. However, there may be staircases or light elements which, you know, if they're being affected by fire, everyone's dead on them. And if they collapse, they're just going to fall onto the concrete slab. Those are less critical. Maybe we can look at leaving those unprotected. Or if they're part of evacuation routes, maybe we need to protect them so they have post-fire capacity. But often there are cable racks or just structural systems that are not carrying load. And also if you've got purlins, etc., as soon as you have thin steel, protecting it is such a mission. And often if it fails, so what? In certain structures, if the sheeting fails, the fire vents up the top and the fire cools down because the hot air goes out the roof, but it will vary from structure to structure. So I was introducing fire scenario. Is it a localized fire, post flashover fire, standard fire, etc.? And heat transfer, how hot is my steel concrete timber? I've skipped entire steps. It's possible to do in a spreadsheet. How hot is a beam, a column, a slab, etc. And run the calcs quite easily and then get to a capacity. It's the same thing as you'd normally do for column design with just a little heat transfer going in the background. Yeah, so that hopefully give you an overview. That's a real crash course. I've condensed our 2-day CPD into 35 minutes or an entire, we have a full 150-hour postgrad course. We're busy with that at the moment, designing bridges for fire and all sorts of stuff. So if you want, our CPD course actually is still online. Because of delays, it's been extended to 12th August and it's 100% online. So if you want to attend that, please let me know. You can just drop me an email. There we go. And you can sign up for that. Other than that, hope you've enjoyed the talk.